Okay, our second lesson is on pressure. Pressure is a rather familiar topic. We talk about pressure all the time, but we'll kind of put some formal definitions to what we mean by pressure. So we define pressure as the force applied to a surface that is, and then divided by the area over which the force is applied. So pressure is basically force over area. But if you have a force, for example, 100 pounds, and it's spread out over an area of 10 square feet, that is not much pressure at all. But if you take that same 100 pounds and you apply it to a quarter of a square inch, that's a huge pressure. So pressure just isn't about force. It's about the concentration of force, the area over which it is spread. So the larger the area, the smaller the pressure. And the smaller the area over which the force is applied, the larger the pressure. So we define pressure as the ratio of force to area. So if you can find the force that's being applied and you divide it by the area over which it is applied, we get pressure. So symbolically, we can write pressure P equals F over A. If you measure the force in pounds and you measure the area in square inches, then the common unit for pressure is a pound per square inch, which is known as a PSI. And the PSI is familiar to you probably if you pump up your car tires, you know they should be somewhere around 30 PSI or pounds per square inch. So that's basically telling you the force that needs to be exerted by the air inside on the tire for every square inch. There should be 30 pounds of force. In the SI system, we measure force in newtons, and areas are in square meters. So the unit for pressure in the SI system is newtons per square meter. And a newton per square meter is defined as a Pascal. This is a very common unit we use. So 1 Pascal, which is abbreviated PA, is 1 newton of force applied over an area of a square meter. Now, a square meter is not very big, and a newton's not very big either. So 1 Pascal can be thought of as sort of a banana that has a weight of 1 newton. And if that banana is spread out over the entire lab table, which is about a square meter, then the ratio of force to area there is about 1 Pascal. So 1 Pascal is really tiny. 1 PSI, 1 pound per square inch, is equal to almost 7,000 pascals. So a pascal is a very tiny unit of pressure. Because of that, typically when we're measuring pressures, we use kilopascals. So just keep an eye out when you see kPa, that's kilopascals or 1,000 pascals. So here's a pressure gauge you might see on an air compressor. The inner gauge right here is PSI, and so a typical air compressor might go up to 80 or 100 PSI. And then you can see the outer ring is measured in kPa or kilopascals. And so that's the way the rest of the world measures pressure. The US uses pounds per square inch, but kilopascals is the standard way of measuring pressure. So it turns out that our atmosphere exerts pressure on us. There's air above you, and that air is pulled down by the force of gravity. So imagine a column of air that is 1 square meter on its base. So that's basically 9 of those floor tiles you see under your feet. That's the area. And on top of that is a huge column of air that goes way, way up into the atmosphere. And it's about 10,000 kilograms or 23,000 or so pounds of air from the surface of the earth all the way to the top of the atmosphere. And all that air is being pulled down on you. So here at the surface of the earth, there's a force on the ground due to that column of air, and we call that the pressure due to the atmosphere. And that pressure turns out to be in all directions around us, and it's about 14 or so pounds per square inch, or about 101,000 pascals, newtons per square meter. Now, this force is really enormous, and later on I'll show you a demo where we will we'll fire a ping pong ball through a bazooka, but we don't really notice this force because it's all around us. We're used to it. Our bodies are adjusted for it. The air pushes in on our skin, so if you imagine a square inch of your skin, the atmosphere is pushing on it with a force of about 14 pounds, but the internal pressure of your body is pushing outwards with the same force, so it's balanced. So we don't really notice that the pressure around us, even though it's quite significant. Because there's so much science that's done on the Earth and at the surface of the Earth, oftentimes when we do experiments, the typical pressure, for example, in a chemistry experiment, is the pressure of our atmosphere. So it makes sense to call uh, a unit of pressure an atmosphere. So in chemistry, PV equals nRT. The P was pressure, and you measured it in atmospheres. So 1 atmosphere is the pressure due to the Earth's atmosphere. If you're doing a chemistry experiment and the pressure is 2 atmospheres, it means the pressure, the force divided by the area exerted by the gas in your flask in your chemistry experiment, is twice the pressure or twice the force for each unit of area of the Earth's atmosphere. So this is a very handy conversion. It's worth pausing and writing down in your toolbox. The pressure due to our atmosphere, which we call 1 atmosphere, is 101,325 pascals, or 101,325 newtons per square meter, which is equivalent to 14.7 pounds per square inch. So you're going to do some conversions. A lot of times we solve problems in pascals, but we want to know what is the result in terms of psi, perhaps, or an atmosphere. So having that conversion is going to be handy. So take a minute to jot that down. So when atmospheric pressure was first measured, it was measured using an instrument called a barometer. And a barometer is a clever little device. It basically is like a seesaw. The atmosphere is pushing down on a bowl of mercury here. And if you make a vacuum in the bottom of the tube here, then there's no atmosphere pushing down on this mercury. The only thing pushing down on the mercury inside the column is the force of gravity. And so the height of the column of mercury is equal to whatever pressure is exerted on the outside by the atmosphere. So basically, a couple 125,000 feet of air pushing down on the outside of the bowl is equal to the same pressure as a column of mercury that is about 76 centimeters or 760 millimeters. And so as the atmospheric pressure varies, as the pressure goes down, this column goes down, and if the pressure goes up, the atmosphere pushes harder, the column of mercury rises higher. So this is a barometer. And because pressure was initially measured using these barometers, it was very common to measure pressure in terms of the height of the mercury column. So 760 millimeters of mercury, for example, would be the height of the mercury column. And so that was also called a torr. And so 760 torrs, or 760 millimeters of mercury, is the same as 1 atmosphere. So if you measure the height of that in inches, you get 29.92 inches. So these are all equivalent ways to measure pressure. So measuring pressure in terms of the height of a mercury column was a historical way we measured pressure, and it's still in use today in some systems, usually involving weather and stuff. So if you grab your weather app and you take a look at it, you'll see that and this is my weather app. It says the rain accumulation, the humidity, and right down here it says the pressure, and it's 30.2 inches, and that is inches of mercury. So that's a way to measure the pressure. And again, here's some more conversions that are handy. 760 millimeters of mercury is 1 atmosphere, which is 29.92 millimeters of mercury. Inches of mercury. Okay, so let's just do 2 pressure calculations to make sure we know how to do this. So to do that, we're going to think about an elephant and a girl wearing high heels and ask which one creates more pressure on the floor. So there's a famous story of some engineers from Boeing who were asked whether it was possible to have an elephant load onto a 747 if the plane was strong enough, and the engineers laughed and said, "Of course it's strong enough to hold an elephant. It can hold a woman wearing high heels." So here's kind of the calculation that leads to that. Let's assume you have a 4,000-pound elephant, so that's 2 tons, and she's standing on 1 foot. And we're going to assume her foot is a circle, and the radius is 6 inches. And we're going to find the pressure that elephant exerts on the floor of an airplane. We are also going to take a 130-pound human who is wearing stiletto heels at the prom, for example. And as she takes a step, all of her weight is on one of the heels. And we're going to assume her heel is a square with a side length of a 1/4 inch. And we're going to find the pressure exerted by the elephant foot and by the high heel shoe, and see which one's greater. So let's start with the elephant. The pressure calculation is fairly straightforward. Pressure is force over their area. So that's going to be the force that's exerted on them divided by the area of a circle, which is pi r squared. 6 inches squared is the radius. So take 4,000 divided by pi times 6 squared, and you get about 35 pounds per square inch. So the pressure on the floor exerted by the elephant standing on 1 foot is 35 pounds for each square inch of floor. For the girl, however, the force that she has is much smaller. She's only 130 pounds, but the area over which that force is much smaller. So if you take the force divided by the area, and the area of a square is x squared, or this side length squared. And so if you've got a tiny little, on the back of the heel here, a tiny little area, it's 1/4 of an inch by 1/4 of an inch, so that's 1/4 of an inch squared. Take 130 divided by that, you get actually about 2,100 pounds per square inch. And so the elephant exerts a pressure of about 35 pounds per square inch, whereas designing an airplane floor to withstand pressures of 2,100 psi is much more difficult. And this is also why sometimes that we don't use, well, oftentimes now we don't use gym floors, because high heels can actually damage the floors. They can actually stress and dent the wood because of the enormous pressures that are exerted, not by very big forces, but by very, very small areas. So that's an example of how you can do some calculations, and you've got some problems to solve with your homework.